Hey class, this is a continuation video where we're going to look at resistors in parallel, where in the last video we looked at resistors in series. I have an example circuit where we have two branches with two different lamps. I'm including the ammeter and voltmeter because we know that that's how they are connected now. We have a battery, which we can call it some V-total. And I wasn't doing this before, but you could include like a potential difference because it is a potential difference across the battery. We know there is a current flowing out of the battery, and that's what we like to call I total. We also say that there's a current flowing through each resistor, I1 and I2. And we'll notice that there's going to be a difference in this situation from between I1 and I2 because of this junction and what that means. That's saying this is R1, right, and this is R2. We also know that there is a potential difference across each of these. I'm only going to write the change of potential of 2 because there's a voltmeter, so it's kind of measurable, but know that there's also a potential difference across the first resistor as well. And I want to look at a circuit that looks like this. We're going to use FET, and we're going to notice what happens to the current and the voltage. I'm going to first start just qualitatively, just looking at kind of how the simulation shows what's happening, and then we're going to use the ammeter, use the voltmeters, and determine what happens. All right, so I've created a 2-bulb resistor in parallel and a 3-bulb resistor in parallel, recognizing that light bulbs act as resistors. One note I didn't make in my last video is that most filament bulbs actually aren't ohmic, which means the resistance may change depending on how much current is flowing through them. But this simulation, that's the only fault to the simulation, is that they make them ohmic. So each of these will have a resistance measured 10 ohm, 10 ohm, and it will not change. So that is a fault that I didn't claim last time. I don't have the single bulb circuit because that's what we've seen before. We have this light bulb, it's bright, it's 10 ohm, and there's a 9-volt battery as seen here. And we'll also have a 9-volt battery here. So one thing that's unique is that in a series circuit, we noticed that the brightness decreased significantly as we added more resistance. That's because it decreased the current and therefore decreased the power transmitted. And also the voltage was distributed among the resistors. So it would be like 3, 3, and 3. So both the current and the voltage are kind of contributing to this lack of power. But in this one, surprisingly, that doesn't happen. Now we want to look at what is different across each bulb in this case. And we do notice that the total current that's coming out of the battery is not the same as the current that's going through each resistor. And so that's the first thing we want to take note of. And then we also notice that the brightness is still pretty big, doesn't drop a lot. So that must mean that the voltage or the potential difference across each bulb might not be affected as much. So I've created this circuit in the FET. I would like you to do the same. And I'm using an ammeter at each branch to tell me the current that's passing through each branch, a current coming out of the battery so I know the total current, and then I have a voltmeter which I'm going to use to measure. We already see that the light brightness of the bulbs are pretty consistent and they haven't decreased a lot since adding more bulbs. And this is a 9-volt battery that I've included. So as it passes through and hits a junction, we'll notice that the current decreases in each junction, and it actually splits, right? Because I have 3 junctions, and each of them are getting 0.9 amps. Well, if I add these together, I get 2.7. So we know that the current is going to be distributed among each. As we move the voltmeter across, we get 9 volts, 9 volts, and let me guess, 9 volts. And that is the same voltage as our battery. So I like to think of a parallel circuit kind of like how water is going downhill. It's passing through a potential difference, a gravitational potential difference. And if that river were to split, it would still have the same downward slope, so the potential difference would still be the same, but there would just be less water in the fork, right? The fork in the river. It would have less water in each new little river. So that's how I like to think about it. Now, you might wonder, well, they all have the same current in each branch, but remember, kind of like the same reason we had before, that's because they're all the same resistances. So if I change the resistance, so we're going to go to 5, 10, and 15, like we did before, then you'll notice that the current is now, is it proportional to the resistance? No, because my resistance is less and I have more current. So there must be some inverse proportionality, another Ohm's law relationship. I is equal to V over R. We'll talk about that. We'll bring that up in some math. But that comes from a very important concept we need to remember, and that current passes through or goes through the path of least resistance. So if there is less resistance in this first branch, you're going to get more current. Even if there's no resistance, all of the current's going to go through there, and no current's going to go through here because there's no resistance. It just wants to go that way. But that can never happen, by the way. That's just because we're in a simulation. So we'll always have some sort of distribution of current. All right, so let's go back to our notes. In each resistor, what do you notice? Well, the current is distributed across each, and I'm going to write like resistor, but it's really the branch. And when I say branch, like this is a branch, this is a branch. Those two are branches because they branch off of this main circuit. What is the voltage? Well, it stays constant. So going back to let's give some variables to this. That means that this total voltage is equal to V1, which is equal to V2, is equal to V3 of each branch. Oop, I should be consistent. I need to include equals the potential difference across V2, the potential difference across V3. And we know that current is distributed, so that means that this total current is equal to the sum of each branch current. And that has to do with conservation laws, conservation of charge. We're going to talk about conservation of energy as well. And this comes up, we'll be using these conservation laws to help us understand circuits, this whole unit. So how is energy conserved in the circuit? Well, this goes back to those takeaways that are true for every circuit. And that is the total power, or the power provided by the battery, the current and the voltage, is equal to P1 plus P2 in this circuit. Now, I want to take this, and similar to what we did in the previous, I want to see how does resistance, how can we combine these resistance? In the previous one, we took this circuit and we said, you know what if we made a equivalent circuit with a equivalent resistance, or R total? And so this comes from, solving for this R total comes from this energy conservation law, where we have power total is equal to P1 plus P2. There are some tricks to use, but I'm going to go the long way. And that is, okay, we have I total times V total is equal to I1 times V1 plus I2 times V2. Now, we saw that our voltage stays constant in this situation, so I can cancel out my total voltage in V1 and V2 if I just divide both sides by, let's say, V. Like all of these could be equal to just like, let's just call it V, right? Okay, so we end up with I total is equal to I1 plus I2. Hey, that's kind of like the distributed across each resistor situation with current. And then we're going to go back to like, hey, what equations do we always remember? I don't have anything. I don't have them written out right here, but I'm going to put them as what I will change in potential is equal to IR. So I know that this is also I is equal to the potential, V divided by R. So I can see this as V divided by R total, which is V total is equal to my V1 over R1 plus V2 over R2. And you can see if I had another one, it would be V3 over R3, right? Let's say like V3 over R3, right? They could just kind of keep on going. But in this circuit, it's only two of them. Now, hey, we canceled out our V's before, so I'm going to do that again. My V's cancel out, and I end up with 1 over R total is equal to 1 over R1 plus 1 over R2. And this is the relationship we have between a total resistance and the resistors in each branch. Be careful though, you might say, well, isn't this just the same as a series circuit? Like, can't I just flip everything and wouldn't that become, isn't this the same as R tot is equal to R1 plus R2? And that is not true. No, it is not equal to that. What it is equal to, so like, no, don't do that, that's bad, is that if we were to inverse the left side of the relationship, the left side of the, what do we call it, equivalence, then we would have to inverse the whole right side together. So that is actually what you would need to do. And you have to be careful. And I would say do practice with playing with some numbers, right? Like if let's say each of these R's were 2, for example, so this would be like 1/2 plus 1/2, I'd end up with 1, and my total resistance would have to be 1 because 1 over 1 is equal to 1, right? So it'd be like, let's imagine like if this is 1 over R tot is equal to 1/2 plus 1/2, and that's equal to 1. That means this must equal to 1. But that's if R1 and R2 were 2 ohms. So what if we plugged in 2 plus 2? That's equal to 4. Those cannot equal each other. So it's really important to know mathematically those two are not the same, and that's why we have the 2 separate relationships for series and parallel. Okay, so we still want that. So this is our relationship, but this is the one that's in our data booklet, like going back to here. There we go. Here are our 2 equations where this is for series and this is for parallel. Okay. Now, let's get some practice using the FET. So I want to create a circuit with a 15-volt battery and a 5, 10, and 15 ohm resistor. I want to use my voltmeter and my ammeter to help me see the potential difference across each resistor, to see the current at each point, specifically across each branch / each resistor, and then the power, calculate the power dissipated at each resistor, and calculate the total power available by the battery. This is just for us to kind of make sense of resistors in parallel. Once we do that, we're going to make a table. So go ahead and make this circuit and make this table. And the good news is I already have it done. So I'm going to give you a second to make this and measure the current and the volts, as well as calculate the power. And then let's check our work together. All right, we have the data with 5, 10, and 15 ohms. My current flow would be 3 amp through the 5 ohm resistor, 1.5 through the 10, and 1 through the 15. And we have voltage difference of 15 in each branch, including coming from the battery. We might remember these equations that are always true, and that the R of a resistor times the current traveling through that resistor is going to equal to my potential difference across that resistor. So I end up with 5 times 3 is 15, 10 times 1.5 is equal to 15, and then 15 times 1 is equal to 15. So that all checks out as well. We also know that there's this one that we could try, but I first want to try to solve this using the way that we just came up with, using this relationship right here. So that relationship is 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So I'm going to end up with 1 over R total is equal to 1/5 plus 1/10 plus 1/15. Or I can see this as, if I inverse both sides, I'll get R total is equal to, and then this calculation of 1/5 plus 1/10 plus 1/15. If you do that using your calculator, you do 1/5 plus 1/10 plus 1/15 first, and then you would invert it. So you'd put it to the power of -1, or do 1 over that answer. and you should end up with 2.73 ohms. So this is 2.73. And then to double check to see if we did it correctly, we would take the 2.73, multiply it by 5.5, and sure enough, we get 15 volts. So that is correct, it is accurate. Secondly, we know is the current should be distributed amongst the branches. So 3 plus 1.5 plus 1 is equal to 5.5, so that checks out. And then we have some more calculations to double check as well, and that is how to solve for power. Well, we know to solve for power, similar to what we have above, power is equal to the current times the voltage. So current right here times the voltage difference across each resistor, that should give us our total power. So I end up with 3 times 15, which is 45, 1.5 times 15, which is 22.5, and then 15. And also then 5.5 times 15, 82.5. Now it'd be really hard to get this wrong because this is just, I think, like the commutative property. 45 plus 22.5 plus 15 gives me 82.5, so that checks out. So we have solved this circuit, it's like circuit Sudoku of parallel circuits. We have solved circuits of series circuits, and we leave ourselves with the takeaways of parallel, and that is, in this case, voltage is constant and current is distributed. And it's true, actually, both of these should say across each, and this is where I like to say resistor, but I really want to say branch, because things might get a little complicated later, and we might have more than one resistor across each branch. So across each branch or across each resistor. And what's always true is that same Vn is equal to In times Rn, and the power is equal to the current times the voltage. All right. So the most important part about this is practice, is making sense of how to differentiate and solve, look at series circuits differently than parallel circuits, really being aware of how resistors in series, actually I can do this, resistors in series kind of slow down the total current that's going on, whereas resistors in parallel, they just kind of split the current, but having constant voltage. But in a series, it both splits, decreases the current, but also distributes the voltage. Knowing that the current would like to go the path of least resistance. So in a series circuit, when you add more resistance, you're adding resistance to the same path. So you're just decreasing that current. Whereas in a parallel circuit, as you increase the resistance of a branch, you are decreasing the desire for the current to want to go down that branch. The current will decrease in that branch. Notice that the current doesn't decrease in the other branches because of the Ohm's law of I is equal to the V over R, and V and R are distinct in each branch. It doesn't matter about what's outside. So that's only going to affect the branch current and therefore also some sort of power, because the current in the main line is decreasing due to conservation. All right, this FET's super helpful to use for your asynchronous work, to just make sense of things. So please, I strongly suggest using that, and I'll see you in class.